Next, we'll talk about support vector machines. They're pretty hard to wrap your head around mathematically, but they're a very powerful machine learning model out there, and they actually do have applications within the world of autonomous vehicles. So let's dive into support vector machines, or SVMs, in more depth. They're very useful for classifying higher dimensional data, where we have lots of different features that we're trying to evaluate together at once, like all the different pixels in an image coming from your self-driving car's camera, for example. The idea is that it finds higher dimensional support vectors across which to divide the data. So from a mathematical standpoint, these support vectors define hyperplanes that separate your data into different classifications. And I'm not going to get into the mathematical details because when you start getting into these higher dimensions, there's really no way to wrap your head around it from an intuitive level. But the thing you need to know about SVM is that it depends on something called the kernel trick. And this is just a way of actually looking at smaller subsets of the data and aggregating those analyses of those smaller subsets over the entire integrated set of your data as a whole. This is a way that we can represent data in higher dimensional spaces to find these hyperplanes that might not be apparent in lower dimensions. So the kernel trick is just a way of making this process of finding the hyperplanes efficient, and also to uncover these higher dimensional separations that you might not be able to visualize in lower dimensions that our brains are more accustomed to working in. And yeah, we got all kind of like meta there with higher dimensions and hyperplanes and stuff. The important point, though, is that SVMs employ some pretty advanced mathematical trickery to cluster data. And it can be very good and effective at handling data sets with lots of features, which you can think of as lots of different dimensions of the data. But it's also a very expensive thing to do, and the kernel trick that we described briefly is the only thing that really makes this practical and possible in the real world. Now in practice, we're going to use something called SVC, that's Support Vector Classification, to classify data using the SVM technique, the Support Vector Machine technique. And there are different kernels we can use for our kernel trick with SVC. Some work better than others for a given data set. So for example, there's the linear kernel, which obviously finds linear patterns and separations in your data. There's the polynomial kernel, which can get more curvy because it has polynomials and not just lines. And the RBF kernel, which gets even more curvy to kind of put things in colloquial terms. Here's an example of those three different kernel types on some data that I was playing with here. What I did was randomly distribute some points in this little graph here, just around some different center points that I randomly scattered around the graph, and gave it some standard deviation around that. So the actual patterns that we're trying to find here for classification are really circular areas given by this radius of different clusters that I threw in there. And this is the attempt at the different kernels of finding those clusters. So you can see the linear kernel is limited to these linear separations between the clusters, and it can't really do a very good job of finding those curvy boundaries that actually exist in the fundamental nature of the data itself, but it does the best it can. We have the polynomial kernel here, which because of its polynomial nature can produce these curves that try to get there a little bit better, and this is getting a little bit closer to reality here. It works a little bit better. We can choose different degrees of the polynomial as well to describe how complicated you want that model to be and just how curvy it can get. Finally, we have the RBF kernel. RBF stands for radial basis function, and that's really just a fancy way of saying that we're basing that kernel on the square distance between the points it's looking at. And this allows us to get more complex curves here that you can see here. And it's starting to get more at those underlying actual clusters themselves. So we're seeing things that are more approximating those circular areas that the clusters were actually generated within. So that's actually looking pretty promising there. However, SVMs and SVC can be prone to overfitting. They're very sensitive to the parameters you give them. So for example, in RBF, we can give it what's called a gamma value that defines just how curvy it can get, basically. And your choice of gamma value can really influence how overfitted your results are to your training data. The gamma value specifies the area of influence of the support vectors, and as you make that smaller and smaller with higher gamma values, you end up overfitting the data more and more. So it's very important to find the right gamma value for your data. So here's some examples on some real data that I ran using RBF. With a gamma of 10, you can see that we're kind of getting toward what the polynomial model looked like. It's a little bit more linear in nature. A gamma of 100 gives us sort of a better result that's, finding overall patterns, but overfitting a little bit here. Those curves don't really exist in the function that generated this test data, so there is some overfitting happening already. And at a gamma of 1000, we're just overfitting like crazy. I mean, we're basically just drawing circles around each individual data point here, and, obviously that's not going to work in a general purpose system at all. So again, this is basically an overfitting problem, and the way that we deal with overfitting is through k-fold cross-validation. So what we do to avoid this situation is use k-fold cross-validation on a variety of different gamma values to try to find which ones come out best. K-fold cross-validation, again, is a way of trying to prevent overfitting by randomizing our training data set into multiple training sets that are evaluated independently and averaged together, so we can't overfit on any one choice of training data. Now, the way that we actually evaluate these different things at once is made easy through a Python class called Grid Search CV. Grid Search Cross-Validation is what that stands for, of course. And that allows us to very easily try out different hyperparameters. That's what gamma is called. It's one of many hyperparameters for a model. And try to converge on the one that actually minimizes the k-fold cross-validation error. We call this hyperparameter tuning. And it's a very common problem in machine learning in general. A lot of these techniques that we use have a lot of different knobs and dials you can tweak, such as the gamma setting. And through hyperparameter tuning, we have to arrive at the best value that does the best job of predicting values in our model, but without overfitting to the data that we're giving it. Let's dive into an example and make it real. And we'll actually do a little bit of an exercise here using SVC. And later on, we'll do a project that's a little bit more directly related to self-driving cars as well.